Assalamu alaikum. In this series, Mr. Omar will guide you through some practice problems to cover all items included in the coverage issued by Emirates Schools Establishment, E.S.E. This is part 2. Have a fruitful time.
السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Welcome back to our series. We are now in part 2. In a tug-of-war competition, two teams tried to pull each other across a line. If neither team is moving, then the teams exert equal and opposite forces on a rope. This is an immediate consequence of Newton's third law. I don't think so. That is, if one team pulls on the rope with force magnitude F, the other team will necessarily has to pull on the rope with a force that the same direction magnitude but in the opposite direction. Now, this is right. It is equilibrium. It is not according to Newton's third law. It is equilibrium. Two forces equal to each other but in the opposite direction, so we have equilibrium. Problem. Now let's consider the situation where three ropes are tied together at one point with a team pulling on each rope. So we have now three teams. Suppose team 1 is pulling due west with a force of 715 newtons, and team 2 is pulling due to north with a force of 3630 newtons. Can a third team pull in such a way that the three teams tug of war ends at standstill? Standstill means equilibrium. That is, no team is able to move the rope. If yes, what is the magnitude and the direction of the force needed to accomplish that? Okay. Now let us draw a free body diagram for the situation. Here we have, this is the point or the system. Put x-axis horizontal and y-axis. X means east and y positive means north. Now the first team is pulling due west in this direction. This is F1. F1 equals 2750 newtons. Due west, so put a minus sign, x hat, and this is our force. This is a vector. Now team 2 is pulling due north, so this is F2 to the north. F2 equals 3630 newtons, and since I need it as a vector, it is in the y direction and it is positive. Now, what is F3? This is the question. If you try to find the resultant force between F1 and F2, it should be something like this. This is the resultant due F1 and F2. So F3 should be equal to this resultant but in the opposite direction. This is F3. By the way, F3 is named as equilibrant. Force. That means the needed force to set the system in equilibrium. So the equilibrium force is the force needed to put the system in equilibrium. And equilibrium means F net equals 0. Now, what is Fnet? Fnet, it is F1 plus F2 plus F3, and we need this force to be 0. Because we have a vector notation here, we can apply this equation into x-axis and into y-axis. So Fx for the first force plus Fx for the second force plus Fx for the third force should be 0. That means F3x equals minus F1x minus F2x minus F1x, here it is 2750 with a minus sign, minus F2x. F2, it is only in the y direction, so the x component for it is 0. So put here 0. The answer is 2750 in the x direction, and it is positive. Now, on y-axis, F1y plus F2y plus F3y equals 0. That means F3y equals minus F1y minus F2y minus F1y, it is in the x direction only to the left, so the y component for it is 0, minus F2y, it is 3630 in the y direction. That's it. So F3y is minus 3630 y hat. Now, if we need to find F3, draw the x component. It is positive, the left. This is F3x. At the end of F3x, draw F3y. It is in the y direction with a negative, so it is downward to the south. This is F3y. And this is our F3. And the angle is alpha. Now the magnitude of F3 is given by Pythagorean, F3x squared plus F3y squared, square root of F3x 2750 squared plus 3630 squared. We didn't put the sign here because we need the magnitude. And the answer will be 4554 newtons. And the direction of it, alpha, it is tan inverse the y component over the x component, tan inverse divided by and the angle is 750 52.9. It is with east to south, so it is southeast. And if you need to write down F3 as a vector, it's easy. It is 2750 x hat minus 3630 y hat. Now let's go to the next question. In a physics laboratory class, 3 massless ropes are tied together at a point. A pulling force is applied along each rope. F1 equals 150 at 60 degrees, F2 equals 200 at 100 degrees, and F3 it's also 100 at 190 degrees. What is the magnitude of a fourth force and the angle at which it acts to keep the point at the center of the system stationary? That means we have equilibrium. This means equilibrium. And equilibrium means F net equals 0 as a vector, and the acceleration equals 0, and the velocity is constant. That was meant by equilibrium. Now, all angles, it is a very important note, all angles are measured from the positive x-axis. This note makes the question easy. That means x components relative to cosine, and to the y component relative to the sine. Let us draw our forces, the x-axis, xy axis. Here we have x, and here we have the y-axis. The first force, F1, it is 60 degrees, F1. F2, 100 degrees, is in the second quadrant. F3, 190, it is in the third quadrant. And we don't know where is F4, the equilibrium force. Assume it is in the fourth quadrant. Maybe it will be in the fourth quadrant or not, we don't know. First of all, make the resolutions for the three forces or the four forces. F1, x, it is F1 cosine theta 1. And F1y equals F1 sine theta 1. F2x, it is F2 cosine theta 2. F2y, it is F2 sine theta y, theta 2. Again, the angles are with the positive x-axis. So the all components in x have cosine and the y components have sine. F3x equals F3 cosine theta 3, and F3y equals F3 sine theta 3. And F4x equals F4 cosine theta 4, and F4y equals F4 sine theta 4. Now the resultant force on x-axis equals F1x plus F2x plus F3x plus F4x, and this should be equals to 0 because we have equilibrium. So we are trying to find F4x. f4x it should be minus all of that, f1x with f2x with f3x. So it is minus f1x, it is f1 cosine theta 1 plus f2 cosine theta 2 plus f3 cosine theta 3. Now you can substitute the numeric values. f1 150 with an angle 60, f2 200 with an angle 100, f3 100 with an angle 190. So f1 150 cosine 60 plus 100 or 200 cosine 100, and f3 it is 100 cosine 190. Use your calculator to find the answer. It is 58.2 Newton. Look, it is positive, so it is to the right. It is on the x-axis, positive, so it is to the right. And now Fy, the net force on the y-axis, it is same as before, F1y plus F2y plus F3y plus F4y. This should be set to be 0 because it is equilibrium. Now F4y equals minus F1y with F2y with F3y minus 150. Now it is sine 60 plus 200 sine 100 plus 100 sine 190. If we use the calculator, the answer is minus 309.5 newtons. It is 300.9 newtons. Since it is negative on the y-axis, so it is downward. Remove the minus and put downward. Now to find the magnitude and direction, we need to use Pythagorean and the function of tan. And first we have to draw f4x and f4y in a superposition like this. f4y to the right, and it is 58.4, 4.2. At the end of f4x, this is x, we want to draw f4y downward because it is negative on the y direction. It is bigger than this, but I will not draw on a scale. 3.5, 309.5, and f4 it should be like this, and this is its angle alpha. f4 equals, as a magnitude, f4x squared plus f4y squared, square root of 58.2 squared plus 309.5 squared, and the answer will be. Now to find the magnitude and direction for f4, we need to use Pythagorean theorem and the definition of tan, as we mentioned before. But before, try to draw some diagram to explain the angle and the direction in which quadrant, first quadrant, second, third, or fourth. Now, f4 of x, it is, as we covered before, 58.2, and it is positive. f4y, it is minus 309.5, so it is in the y direction, negative y direction. So draw first f4 of x to the right, then draw at the end of f4x f4y downward. This drawing is not in scale, because if you need to draw it in scale, you need to draw f4y 6 times f4x. Here it f4, obviously it is in the fourth quadrant, and this is the angle alpha. Now, using Pythagorean, f4 as a magnitude equals f4x squared plus f4y squared, square root 58.2 squared plus 309.5 squared. We don't put the signs here because it is a magnitude. If you use the calculator, it should be 315 rounded طبعا. Now alpha equals tan inverse the y component over the x component to find the angle with x. If you need the angle with y, make f4x over f4y equals tan inverse 309.5 over 58.2, and the angle is 79.4. It is rounded. This angle under the positive x-axis, but we need it with the positive x-axis in standard form, so it should be counterclockwise like this. This is the angle needed. So we'll express alpha in standard form as 360 minus 79.4, which is 280.6, I think, with positive x-axis in standard form means counterclockwise. And if you need the factorial form of f4, is 58.2 into x hat minus 309.5 y hat, and the unit is Newton. That's it. Now let's go to question number 3 for this part. We have considered the following simple situation of one object, a laptop computer supported from below and held to at rest. Now let's look at two objects at rest, two books on a table. The figure shown. What is the magnitude of the force that the table exerts on the lower book? Let us draw the three-body diagram for the situation. This is the tabletop, and this is the lower book and the upper one. Now, what forces exerted in each of these objects? First, the first object has a weight, the gravity will pull it down, Fg. We'll name this object 1 and the other one is 2, so Fg1. There are two other forces exerted on the lower table, the book, which is the force due the weight of the upper one, Fg1, and the normal force because of the table. And then we have normal force from the lower book on the upper book and normal force from the upper on the lower book. To make it clear, let us draw each object separately. For the object number 1, which is the lower one, we have Fg1 due the earth and Fg2 because of the upper one and the normal force due the table upward. There is another one which is object number 2. It will be affected by the gravity Fg2 and a normal force from object number 1 into object number 2. This force has a reaction downward here and 2 on 1. So this is the free body diagram for the two objects. Question number 3 here. The two blocks are in contact on a frictionless horizontal tabletop. An external force F is applied to block 1 and the two blocks are moving with constant acceleration of 2.45. Use mass M1 for the blue one 3.2 and M2 for the gray one 5.7. What is the magnitude F of the force applied? First, let us discuss what forces exist in these two objects. When we pull or push M1 with the force of F, M1 will push M2 with a force in this direction. It is a normal force from 1 onto 2. M2 will push M1 back with a force of N21. And according to Newton's second law, N21 as a vector equal minus N1. There are other forces due gravity, Fg1 and Fg2, but these forces will not affect the acceleration of motion and the normal the table in 2 and in 1. These four forces N1, N2, Fg2, Fg1 will not affect the acceleration of the motion to the right. So, to find the magnitude of F, let us apply Newton's second law on the whole system. Newton's second law says that F net on x-axis equals m times a. What are forces acting on the system? We have F to the right, then N21 to the left, and N12 to the right. So these forces are F to the right is positive, minus N21 plus N12 equals the mass of the system is M1 plus M2 times the acceleration. Now N12 and N21 will cancel each other because they are equal in magnitude and opposite in the direction. We are left with F. It would be equal to M1 plus M2 times the acceleration. Substitute the values. M1 3.2 plus M2 5.7 all multiplied by the acceleration was 2.45, and the answer will be 3.2 plus 5.7 times 2.45. It is 21.805 newtons. If we apply the rule of significant figures, it would round it to 21.8 newtons. This is for the first one. What is the contact force between the blocks? For the contact force between the blocks, we need to find N12 or N21. To do so, take M2 as a separated object. So P, we need to apply Newton's second law but now on only M2. M2 is affected by the force N12. That's it. There is no other force acting on M2. Now, Newton's second law says that F net on the x-axis equals m times a. I need to apply only over M2. F net over M2 is N1. M2, it is 5.7 times the acceleration 2.45. And the force would be 13.965, almost 14 newtons. What is the net force acting on block 1? Again, Newton's second law. C. Newton's second law on M1, F net x-axis, m times a. We need only the block number 1 times a, and F net x. Now M1 it is 3.2 times the acceleration 2.45, and the answer will be 7.84. Or we can do this F net on the object M1 equals, this is object M1 affected by N21 and F to the right. So it is F plus minus N21. We find F is 21.8 plus times minus minus N21 is the same as N12, which is 14. Now make the subtraction. 21.8 minus 14, the answer 7.8. same as this. Now we have situation of snow border. We will discuss this question in two situations. First one, without friction, this problem. The other one with the friction, this problem. Okay, now let's start with this. A snow border mass of 72.9 and height 1.79 glides down a slope with an angle of 22 with respect to the horizontal. If we can neglect friction, what is his acceleration? We need to draw the free body diagram for this guy. This is the slope. The angle is 22. Here is the system, which is the snow border. X-axis parallel the surface of motion. Y-axis normal. Now forces are Fg, which is mg, the center of the earth. And since the inclined here, the angle is 22, we can put it here between the weight and the y-axis. And we have the normal force on the y-axis. And there is no friction. The motion is down the incline. This is the motion. No other forces acting on the snow border. Now, there is no friction, no need to find the normal force. Since there is no friction. So go immediately on the x-axis. F net on the x-axis should be m times a, which is the Newton's second law. Before we continue, we need to make resolution for Fg into y-axis, Fg x, and into y-axis Fgy. Fgx equals Fg sine theta, and Fgy equals Fg cosine theta. Why this is so? Because the angle is between y-axis and the Fg, so the y-axis represents the adjacent, so it will take the cosine, and the x-axis will represent the opposite, so it is relative to the sine. Fg, it is mg, then we have sine theta. On the y-axis, mg cosine theta. Now go back to Newton's second law and make in consideration only the x-axis. We have only one force. It is Fgx, and it is in the opposite, in the positive direction. Fgx equals m times a. Fgx is mg sine theta equals m times a. We can cancel m since m is not 0, and the acceleration will be g sine theta. This result is a fact in physics. If any object is sliding on an incline without friction and without any other forces, the acceleration always equals g sine theta. So you can put this immediately in such a questions, but put in consideration we can apply this formula if there is no friction, no other external force. If these two conditions are satisfied, then we can apply this equation immediately. 9.8 sine 22. And that's it. The answer would be 3.67 meter per second. Now, we need to consider the friction force. Let's reconsider the snowboarding situation from solved problem, the previous one, but now include friction. A snowboarder moves down a slope for which theta equals 22. Suppose the coefficient of kinetic friction between his board and the snow is 0.21, and his velocity, which is along the direction of the slope, is measured as 8.3 at a given instant. So we will consider this as the initial velocity, and that one is the coefficient of friction. Now, again, we need to draw the free body diagram for the situation. This is the incline of the slope. The angle is 22. This is our system. X-axis parallel to the surface. Y-axis normal to the surface. The gravity downward to the center of Earth. This angle is 22. Now make resolution for FG. The x-axis FGX. The y-axis FGY. FGX equals FG sine theta, and FG is mg sine theta. And the y-axis FGY equals G cosine theta, mg cosine theta. Again, theta is with y-axis and the weight. So the y-axis represents the adjacent. We'll take the sine. Now, other forces is the normal force. Is always on the positive y-axis. And now assign the motion. The motion is down the incline. This is the motion. Since the motion is in the positive x-axis, then the friction would be in the negative, and it's a kinetic friction. Since we have friction, we need to find the normal force. Now, on y-axis, apply the equilibrium condition. F net on y-axis should be equal to 0. Now on y-axis we have only the normal force, the positive direction, and FGY in the negative direction equals 0. So the normal force equals FGY, which is mg cosine theta. Since we have the normal force, we can find the friction. The kinetic friction, Fk, equals mu k times n, which is mu k times mg cosine theta. Now if we go to x-axis, on x-axis, apply Newton's second law. F net on x-axis equals m times a. On the x-axis we have two forces. We go to the x-axis, we have two forces, Fgx to the right, Fk to the left. So Fgx positive minus Fk negative equals m times a. Now we need to find a. Put Fgx as mg sine theta minus for Fk mu k mg cosine theta equals m times a. Since m appears in all terms, we can divide by m, then the acceleration will be g sine theta minus mu k cosine theta. We factorize the g. 9.8 sine 22 minus mu k, it is 0.21, I think. Yes, 0.21. Cosine 22, and the answer will be 1.76 meter per second square. Now the question needs to find the speed, assuming a constant slope. What will be the speed of the snowboarder along the direction of the slope when he is 100 meters further down the slope? Now we need to use equations of motion, and we need equation that has delta x and acceleration and v initial and v final. So we will use v final squared equals v initial squared plus 2a delta x. The initial speed, it is 8.3 in the positive direction, squared plus 2. The acceleration is 1.67 and delta x is 100. It is along the slope downward, so it is in the positive x-axis, so it is positive. The motion is along the positive x-axis, alhamdulillah, so the acceleration is positive. From this we will find v final equal plus or minus, take the square root of the expression, it is 20.5. And since the motion in the positive x-axis, so take the positive sign. Positive x-axis. Now problem number 2, the same question. How long does it take the snowboarder to reach this speed? We need another equation of motion, including the time. We can use v final equals v initial plus at, or delta x equals v initial t plus 1/2 a t squared, or delta x equal 1/2 v initial plus v final times t. Any one of these equations will be used. So I will use the first one. 5 equals v initial 8.3 plus the acceleration is 1.69 times t. So the time is 8.3, 6.95 seconds. Now the last idea for this question is, given the same coefficient of friction, what would the angle of slope have to be for the snowboarder to glide with constant velocity? Now the constant velocity means the acceleration is 0. We know the expression for the acceleration. It is g sine theta minus mu k cosine theta. So from problem 1, A equals g sine theta minus mu k cosine theta. Again, this is the expression we need. Now the acceleration is 0 for constant velocity. So put here 0 equals g sine theta minus mu k cosine theta. That means sine theta minus mu k cosine theta should be equals 0 since g is not 0. Then mu equals sine theta over cosine theta. Maybe you remember this equation from part 1, video part 1. So theta equals tan inverse of mu, tan inverse of 0.21. It is 11.9 rounding, 11.9. So for this snowboarder, we need a constant velocity, which means equilibrium, the x direction, which means acceleration is 0. Theta should be 11.9. Let's go to the next question. This question includes Atwood machine. For the shown Atwood machine consists of two hanging weights, 1 and 2, connected via a rope running over a pulley. Consider friction free. There is no friction. Where the pulley do not move and the rope glides over it, and assume that M1 is greater than M2. If M1 initially at 2 meters above the ground, derive the formula to find the acceleration A of the system. If M1 equals some, M2 equals 3, how long it takes for M1 to reach the ground? Let us take the system as a whole. Since M1 is greater than M2, then M1 will go down and M2 will rise up as indicated here. If it is not indicated in the drawing, we can conclude it. Then assume that we have an axis like this. Any force with this axis should be positive, against it should be negative. Now, what are forces acting on the system? For M1, we have gravity downward, Fg1, and for M2, Fg2, and we have a tension in the rope in both sides. Now, these two tensions are equal because we have the same rope without friction, without anything else. So T1 equals T2. Then take in consideration that T1 equals T2 equals T. Now immediately apply Newton's second law on the whole system. F net equals ma. Follow me carefully. Start with Fg2. Fg2 is against our axis. We assume that the axis here is up. here is to the right and there is down. So Fg2 against this axis, so we would minus Fg2. Then we have T1 and it is in the positive direction, plus T1. Then we have T2. It is against this direction, so it is negative T2. Finally, we have Fg1. Here Fg1, it is in the positive direction because here the positive direction is downward. So this to the right, the positive is downward, and to the left, the positive is upward because the motion is clockwise. So we have plus Fg2, Fg1, sorry. All of these equals the total mass, which is m1 plus m2 times A. As we mentioned before, T1 equals T2, so they will cancel each other, minus Fg2 is m2g, plus Fg1 it is m1g, equals m1 plus m2 times A. Now g, as a common factor, it is m1 minus m2. I started with the positive m1, then minus m2, equals m1 plus m2 times A. Then the acceleration is m1 minus m2 over m1 plus m2 times g. You can, for Atwood machine, use this expression immediately without reproduce this equation. Now we have the acceleration. Acceleration equal, substitute now, m1 is 5 minus m2 2 over m1 plus m2 times 9.8. So it is 3 times 9.8 divided by 7, which is 4.2 meter per second square. Now, if we need to find how long it takes m1 to reach the ground, we have the acceleration and the initial velocity is 0 from rest, and we need the time. Use this expression, delta x equals v initial t plus 1/2 a t squared. V initial 0 times t plus 1/2. The acceleration is 4.2. It is in the positive direction. For m1, the positive direction is downward, times t squared, and the total distance to be covered is 2 meters, because it is 2 meters above the ground initially. Then we can find t. T equals 0.976 seconds. As an addition, suppose that the question needs you to find the tension in the rope. Find the tension in the rope. You can use either M1 or M2. I will use M1. This is M1. Don't forget, for M1 the positive is downward, and M1, as shown before, is affected by two forces, Fg1 and T2, which is T. So we have here Fg1 downward, which is m1 times g, and the tension upward. Don't forget the acceleration is downward here, positive. Now put Newton's second law, F net equals m times a. We have m, it is m1. A It is M1 minus M2 over M1 plus M2 times G. If net, the tension is upward, which is opposite to the direction of the axis, so minus T plus FG1, which is M1G. So F net equals minus T plus FG1. We need now T1, T equals M1 G minus M1 times M1 minus M2 over M1 plus M2 G. You can now factorize M1. Here, if you take M1 as a common factor, left with 1 minus M1 minus M2 over M1 plus M2. And this one will be M1 times G, M1 plus M2 minus M1 plus M2 over M1 plus M2. Now you can cancel M1 and you are left with M2 plus M2, 2M2. So it's 2 M1 M2 over M1 plus M2 times G. Again, you can use this immediately for the Atwood machine. Find the tension. Substitute and you will get the answer, which is 28 Newton. Again, you can find it immediately from here if you substitute for Fg M1 5 times 9.8 and for the acceleration 4.2 and here 5. If you put this here 5 times 9.8 and here 5 and for the acceleration 4.2, without this expression you will find the same answer. Thank you. See you next part.
I hope that this video has enriched you more. In the description box below, there are links to both a PDF document for answers and the other videos in this series. This is the end of part 1. See you in part 2. Salam.